Okay, good afternoon. Welcome to the ISCS 6D, and I will talk about structural hold on, I guess structural induction and structural recursion. So structural using recursive definitions to define other objects than so far we have used recursion to define functions. We use recursion to define algorithms. These were recursive algorithms. We use recursion to define sequences. But you can use recursion to define other basically general data structures. And that's what I will be talking about today. And just let me bring it up. Okay, so this corresponds to in the textbook, it's chapters 8.8 and 8.9. Okay, let me, hopefully this will focus a little better. Okay, okay. So let's start a little bit like with stuff that is just to recall things, right? So, so here is the recursive definition of factorial function. Okay, so a factorial is a function from takes any positive integer and outputs an integer. Okay, and we can define it like this. In the base case, so n equal 1, we define f of 1 to be 1. And in the recursive case, so for n greater or equal to 2, excuse me, we define f of n to be the product of n and f of n minus 1. Okay, and if you work this out, right, so I call it, I ask, okay, what's the function at n? Well, it's n times the previous value. So what will be this? This will be n minus 1 times the previous. And that will be n minus 2 times the previous, and so forth. And if you work it out, this is just the product of consecutive integers starting from n, then a smaller one, then a smaller one, until you reach the base case. So this does define n factorial, right? Which is n times n minus 1 times n minus 2, dot, 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 to 1. So this is a closed form, right? For the same thing. You can define, say, power of a. So integer powers of with base a, right? So for n equal 1, I would define this function to be just a. And into recursive, so for n greater or equal to, I'm not going to write this. So this is the base always, and this is the recursive. F of n will be this constant a times the previous value of the same function. So what does this define? This a to the power of n. Why? Because this is just a times and how many of these recursive calls have I made? Well, n, because that's what it takes. Every time I call it, I decrement the value until I get to the base case where it's wait. So this is n times, right? And so this is a to the n, or let's say multiplication of a, right? So I do the same, but for addition, a plus fn minus 1, and of course I accumulate additions this way, so fn will be a times n, right? And clearly, you know, these recursive definitions, well, this is basically straight away you can see that this is a recursive code, right? This is recursive algorithm. So compare to recursive algorithm for factorial, right? So how would I write basically the same thing as an algorithm? Well, I would say algorithm factorial on input n, and I assume n is greater or equal to 1 in here, right, would do what? If n is 1, return 1, else return n times factorial of n minus 1, right? And end of story, right? That's the whole code. And this exactly, it's 1-to-1, right? Like this thing is this thing, and this thing is exactly this thing, right? So here is my base call, here is my recursive call, and here is the base, and here is the recursive, right? So 1-to-1 correspondence between a recursive definition of a function and recursive algorithm that computes that function. Okay, but let's now use similar recursive thinking to define other things than functions. Okay. Okay. So in general, I can I will first explain it as a recursive definition of sets, but actually you can have other recursive data structures than sets. Okay. So recursive definition of set, and I'm going to call it S, but here S is just a variable, just a variable name, okay? So don't be tied up by calling this S. You can call it A, you can call it B, you can call it whatever you want, and we will see some examples where we'll call these sets for different names according to their semantics. Okay, so recursive definition always includes 3 things, the third of which, though, is almost always used, is implicit because it's always the same. So first, it must have some basis rule. What does that do? Well, we specify some elements of S explicitly. Okay, so we just explicitly. Okay, we declare some elements as members of set S, and then we have this recursive rule specifying new elements of S as functions, as some functions, or it could be just one function, but it could be many of existing elements of S. Okay, and the third thing is so-called exclusion statement. Okay, and it's like a legal contract, so therefore it's basically implicit, that says this exclusion statement says always the same thing: S contains only elements created by base rule or some number of applications of recursive rule or its rules, because in fact these are rules. So this could be many specifications of this type. Okay, but they're really okay, I guess it doesn't matter whether you specify new elements as a bunch of functions or you have many such specifications. Okay. All right. So let me give you an example. Okay, so first example we'll look at is the same as in the book, which is let's define set I'm going to call it PNPS, which is a set of all properly, so it's a set of all properly nested parentheses, parentheses strings. Okay, so PNPS. Let me give you an example of what I mean by properly nested parentheses string. Okay, so for example, this string, okay, it's a string, it contains 2 elements. Okay, like here is a little dot between the first element and the second. Well, this string is in the set. Okay, another string is this one. Okay, that's also in the set. Okay, so these are strings over an alphabet that contains only 2 elements. Okay, open bracket symbol and a close bracket symbol. Okay, these are the only 2 symbols that you can use, and you can use any number of them. Okay, so what is this notation? It's a set of 2 elements, and I can take substrings of arbitrary length, right? So you should remember this notation for strings over sets. Okay, so so here is an example, right? Like S is this thing, the length of S is 2, and is this thing, its length is 4. Okay, so S belongs to this set to 2. Yes, because it has 2 elements. This guy is in here, and this guy is also in here. Okay, I guess I'm just hopefully you're with it. Here is another string that is in the PNPS, in the string of properly nested parentheses strings, in the set of properly nested parentheses strings. Okay, but something like this, open, open, close, is not. Or some weird stuff where I close and then open and close and then open. No, well, I don't like this. It's out, right? Okay, so how on earth am I going to define properly nested strings, right? Like properly nested parentheses strings. I cannot enumerate them, and yet I intuitively know what it means, right? Like I have to, if I open, it has to be followed eventually by a close, but a close that corresponds to it, right? So, if I'm opening, then that's okay, as long as I close. And, so this thing, right, is in the set. But, when I see open, and close, and I see close, I'm happy and I'm kind of done. But if I don't see the close, but another open, I'm okay. I just remember that eventually I have this open that I have to close. Okay, so I can parse these strings, but what am I really doing, right? Like, what's the algorithm for recognizing these things? Okay, well, here is a simple recursive algorithm. So here is the recursive definition of the string, of the set of properly nested parentheses strings. And because it's recursive, so it will have 2 elements, basis and recursion. So in the basis, okay, I'm just going to say that this thing is my atom. Okay. In fact, there's many ways you can have this definition, and it will define equivalent objects. So I'm just choosing one definition, and let's go with that one for the time being. So the recursive rule is actually 2. So it's recursive rules. My first rule is that if A is a properly nested parenthesis string, then so is something built like this. I open, then I concatenate A to it, and then I concatenate a close. And that is also in this set. So again, what is this? This is a concatenation of this string A. So this is just an element. And this could be just, it could be a string. It could be also just an element, or it could be a string. And this, right? And this is just, it is another element. Okay, so it's a concatenation of these three things. This is a constant, if you want, and this is a variable. Okay, but that's not all, because in this way, well, I can, this object is an application of this rule where little a is distinct. And little a is distinct and therefore is declared to be an element of the set. But I cannot really generate strings like this using this formula. Okay, so I add the following. If A and B are both elements of this are both properly nested parenthesis strings, then so is AB. Okay, so what is this? This is a concatenation of string A and string B. Okay, so this is in brackets because, you know, I'm just telling it to you like a secret, but it's not, you know, it's like you don't even need to write this. Okay, so I need to write this for you because, you know, it's a lesson, right? But you don't really need to write this. And a third thing is this exclusion statement, which says that, you know, nothing else basically is in PNPS, right? So that's what the exclusion statement means. It's always the same. It's just a copy of this text, regardless of the basis and recursive rules. It just says that these rules are implications. If something belongs, then something also does. Implications don't exclude some strange facts like that, you know, if a string made of 1, 2, 3, 4 belong to PNPS, it would not violate either the basis rule or any of these implications, because it doesn't matter that that you would never create 1, 2, 3, 4 on this side. Is my internet connection okay? It's a question to students.
It's constantly the camera is always blurring and the voice is cutting off, like it's doing that every single 10-15 seconds.
Okay, you know, let me try.
The camera is fine, the position is fine, it's just the internet connection, and right now you're completely frozen.
Yes, because I changed the connection to a wired one. Do you guys hear me any better?
Yeah, we can hear you fine.
Okay, let's try to go with the wired connection. It's slower, but I think more reliable. Okay, so let's. So these are this is my recursive definition of PNPS. Okay, it's very concise, right? It has only the base case like this, and these simple implications as the recursive rules. Let me copy this on a new page. So so PNPS definition would be first, so the base is that this is in PNPS, open close, and the recursive rule is that if A if A, B are in P and PS, then first of all, this thing is in P and PS, and the second rule was this. Sorry, this is another notation for concatenation, but let me use the same notation as I used before. Okay, so that's it. That's the full recursive definition, and there is this implicit exclusion statement, which I'm not going to repeat now. So let's see. So you can look at this like this. Consider it was said that the way recursive definitions work is that the only things added to the set is something that is added by the base case or by the application of one of the recursive rules, and perhaps recursively, right, as the name suggests. So let's see what is created. Let's look at the number of recursive rule applications and look at the PNPS set created so far. So if I don't apply any recursive rule at all, so then the only thing that is in the recursive in the PNPS is this string, right? Because this is declared by the base case. Now let's use the recursive rule just once. Okay, so I take what is in PNPS. Well, both A and B have to be equal to this string because that's the only element of PNPS. So A is this and B is this. And what do I add to PNPS based on this single application of the recursive rule, where I add, okay, so let me first of all say that whatever I had in the set is already in it, okay? But what am I adding now? I'm adding open and A, and the only A was this guy, right? So it's this thing, and then close. So this is what I added. You know what? So let's change this to saying new PNPS elements created so far. I think this will be clear because then I don't have to repeat the previous ones. So I'm going to add two elements. This element where A is an element of PNPS, so it has to be this. I created that. And also this thing. But what could this be? Well, the only element PNPS so far is a singleton that contains this. So both A and B have to be equal to this. So therefore the concatenation is this string. So these are the two new strings which I added to PNPS by a single application of the recursive rule. And if I use the recursive rule twice, then okay, so I added, so this is how many elements I added by no applications of recursive rule. So therefore it's a base case. This is a single application. These two were added. Let's apply recursive rule once more. And now, well, so what can it be? Now A and B can vary. A could be this, this, or that. B can be this, this, or that. So let's go in order. Let's make A and B both equal to this. Well, I'm going to add this and this. So that was the case where both A and B were equal to this guy. Well, I didn't really need to look at this. This is the same things that were already added by one application. All right. So let's look at A this and B that. So I added this, right? So this is my A and this is my B. And they were both in the set. So this I don't really have to look at. Let's now A be this and B be that, right? So what did I add? This. Here is my A, here is my B. In this application of the recursive call, A bound to this element and B bound to this element, and this is a concatenation of A and B. Okay, what else can I add? Well, of course, A can be bound to this and B can be bound to that, right? So, so here we go. This is A, this is B. Of course, I can switch them. So how about this, right? So this is my A, and this is my B. Also, I can double these guys because let's like this. So this is my A and this is my B, or like this. Sorry. This is my A, this is my B. Sorry, this was horrible. So open, close, this is A. Open, close, this is B. Both of them are in the set, right? So I can, the single application, one more application of this recursive rule is going to add the string. And I'm probably not done. Yes, probably there's ways to bind these that are going to, like, for example, how about this and that, right? So, oh, okay, I already did that. Now, if I take A this and B this, I'm going to get the same, right? So I can also look at this like that. This is A, this is B, and it will output the same element. Is that a problem? No, because adding the same element twice to the set is no problem for me, right? It's still the same set. Okay, so you can see that basically even very few applications of these recursive rules start generating huge amount of stuff. You know, why is that, right? So basically, you know, this is going to be now even a more complex set, right? Where I take all iterations of possible choices of A and B's I have and creating more stuff, right? So you can think of this generation of all PNPS elements, in other words, all properly nested parentheses strings. Well, you start with this guy, and then you apply rule number 1 to get this, and you apply rule number 2 to get this. Now, well, the thing is that this doesn't have, you know, really a binary tree structure, right? So
please move the paper down a little bit so we can't really see it. Thank you.
So here is, it doesn't have a binary tree structure, right? It's let me try to because now I can bind my variables to any of these, and you know, first of all, I can use R1 to all of them, right? Using R1 to this one does not matter, but I can now take any two and use the rule R2, and also switch them, right? Because the rule R2 is really, you know, if this is my A and this is my B, I get one thing, but if this is my A and this is my B, I get another thing. So it's really like this. So it's, you know, it basically is just going to grow into this huge graph, right? But yet the code is very concise, all right? You can also, another way to look at this is that you can, so here's the PNPS definition again. It's so short, I can repeat it. I can write it very fast. The recursive rule is that if A, B are in the set, then so is this, and also this are also in the set, right? So perhaps I should say here and, right? So these two strings are in the set. Okay. So recursive definitions as code? Well, the first view is that the recursive definition generates all elements in the set. So elements of the set, right? But another view is that recursive definition recognizes all elements of the set. How so? Well, rather than go from base, like in this example, right? Like I started from the base and I ran the rules and I just look what is the set of this huge amount of stuff that is generated, and then I apply these rules some more and look at even more expanding set of what, and I can ask the following questions, which is some string s in the set, so for example PNPS, right, in the recursively defined set. So this corresponds to walking. I can do this by walking backwards. So let me give you an example, okay? Let's say we ask, is something like this: open, open, close, open, open, close, close, close. Is this an element of PNPS? Okay, let this be a question. I mean, you can parse it on your own and see, yes, right, it should be. But now, how do we exactly use these rules? So, well, I can start, basically, I will start with this string on the bottom. And, well, how can I tell? Well, it is not, okay, it is not added, it's not a base case string, right? That's a check, it's easy to tell. So if it's in the set, it has to be either of this form or of this form, where these things are both in the set. So I have, I can basically, this would follow, this would be in the set, this would be implied if by rule number 1, so by recursive rule number 1, okay, by this rule, so this is the recursive rule number 1, and this is the recursive rule number 2. If the inside of this, namely this thing, was in the PNPS, right? Because if this thing, sorry, and I made a mistake. Okay, what's inside? Open, close, open, open, close, close, open, open, close, close. Okay, because if this string was in the set, then the first recursive rule would bind A to this element, would generate this element, right? Because this element is whatever this thing is, A, with open, A, close. But that's not the only possible way to generate it. Perhaps this could be generated by recursive rule number 2, applied to some substrings of this, right? So perhaps this is A and this is B. So this would be implied if the following thing was in PNPS and the B, which is open, open, close, 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 was PNPS. Now, of course, you know, and I know that these things are not. But an algorithm, a recognizer that just applies these rules would not. So this is really a bunch of, right? How many such statements, such implications would there be? As many as these parsings. So this would be also follow if this is in PNPS, and the rest, which is open, close, open, open, close, close, close. And it would be also implied if open was in the set, and after that is close, open, open, close, 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 right? So how many of these there are? 1, 2, 3, 4, 5, 6, 7, 8. I guess 8 or so, right? Depending on how I parse. You can sort of see in your head that none of these is going to be true. So all these rules are useless, really, but an algorithm won't know it. The only productive way is to rewrite this in this form, and then this would be implied if this thing was in PNPS, and also this thing was in PNPS, but by recursive rule number 2. But you can see that also this is implied by all sorts of other stuff, like, for example, that this is in PNPS and the rest. Now, we know that this is not true, but sort of the algorithm that parses doesn't. And now this is by base case. And of course, you and I know that this would be by recursive rule number 1. It would follow if this thing was in PNPS, right? Because this is now your little a, and this is open, a, close. And this is by base case. So this path this is true, this is true. These two statements are true by base cases. This is therefore true by application of first rule. This is therefore true by application of second rule. And this is therefore true by application of the first rule. And we are done. The answer is, answer is yes. Right? The answer is true. And the fact that all these other parsing are not productive, well, so what? These are implications. So it's quite okay for all of this, all false. I don't care. Okay. Now, as a computer science type of person, you will ask, well, okay, this is horribly inefficient. You know, to test whether or not something in a set, I clearly have like so many choices. And every time I move up, my choices go right. Well, wasn't it similar as in the case of going down, right? When we were trying to go down to see, you know, the string that I was asking about, right? The string open, open, close, open, open, close, close, close is somewhere in this huge set. Either procedure is horribly inefficient, but you know, but it exists, right? So what's the bottom line? These things are incredibly concise and economic, so to speak, in stating, in defining some things which are not trivial, okay, to define. They don't necessarily, they both translate into algorithms for generating elements of such sets, and also for algorithms that recognize whether or not a given element is a given object is a member of the set or not. Neither of these are guaranteed to be efficient. So you could ask, how do you write these rules to have efficient algorithms? Okay, so this is, look, let me just show you that this is not set in stone. You know what what was our PNPS definition? You know, this definition of the set of properly nested parentheses strings. It was just had 2 lines. This is in the set, and also if A, B are in the set, then so is this, and A, B are both in the set, right? This was our definition. And here is look, here is an alternative definition. PNPS alternative definition. An empty string is PNPS. So lambda is denotes empty string. Okay, it's a special symbol. Just like we had a special symbol for denoting an empty set, we are going to have a special symbol for denoting an empty string. And the recursive rule is the same. So here is the alternative definition. These two definitions are clearly not syntactically the same. They do have the same recursive rule, but they don't have the same base case. What's the, I'm going to call it PNPS plus. What's the relation between PNPS plus and PNPS? I'm opening the floor. Whoever wants to say what's the relation between these two sets is welcome to do so.
They are the same set, are they?
Okay, there is one tiny difference.
There's an empty set included, right?
Who can see a difference between these sets? They are almost identical. There is one of them has one more element than the, I mean, has an element that the other does not. Yes, I see people on the chat have said it. So PNPS plus is a union of PNPS and one more element, an empty string. Okay, right? This, by the way, is something that you can convince yourself by induction. And this type of induction we will call structural induction. So it will be inductive reasoning, but applied to recursively defined objects and not to integers. Although the way you can map it to the standard induction by just mapping the number of recursive rules used to an integer. And the statement that you're going to prove is that for any element created by this using n up to n recursive rules can also be created like this using n recursive rules, and any element that can be created like this using n recursive rules is either an empty string or an element that can be created using n recursive rules. So these are really proofs by on integers. Okay, just so this would be a standard rendering of a proof of this property, where the induction parameter is the number of recursive rules used to generate anything here. Okay, and anything here. Okay, and there is way more. Okay, so in fact, you can ask, for example, let's say PNPS question mark to be defined like this. Close open is in PNPS question mark, and if A and B are in PNPS question mark, then so is A this, and let's say this are both in PNPS question mark. Here is PNPS double question mark, or yeah, empty string is in the PNPS double question mark. And if A, B are in P and PS double question mark, then so is open A, and also A, open A close, open B close. What are these things? Okay, these are recursive defined sets. They all look very intuitive, you know. It's like, how come these are the only production rules? You know, somebody could very easily give these production rules. They seem supernatural, right? And who says that you should start from this? Maybe starting from an empty string. Yes. These rules are, as you can see, incredibly concise, right? Very simple. And yet, seeing, are they equivalent? Which one is, you know, okay, there's no question of better. It's just that, do they all generate, you know, whether you treat an empty string as a properly defined, properly nested parenthesis string, it's like, okay, I can, or I, you know, I can either declare it as you know, as correct or not. All right. And a person on the chat said yes, that this PNPS question mark would not generate, so it does not include something like this. Right, I cannot interpret this way because then my A would be okay, sorry. No. Oh God, I didn't render it correctly. Open, open, close, close, open, close. So clearly it's not the case of this, right? Because this inside is not properly nested. And how do you parse like this? Well, the only hope of parsing is this way. And oh no, it is. Yeah, sorry. This is true. Okay, yeah. Somebody suggested this on the chat that is not a string, but it is, right? Because this guy in here is like that for A equal this, which is in here by the base case, and this guy here is in the base case. So I can still generate the string. Okay, so I will leave you with these question marks, right? I will post these notes, and you can sort of think: are these the same? Are these not the same? What's going on? Okay. So let's move to some to a different example. Let's define the set. So let me give a recursive definition for B star, which is a set of all binary strings. Let me recall some notation first. So bits, I'm going to say, is the set of bits. Okay, so this is the set of bits. Okay, bk, b to the k is the set of k-bit strings, and b star is the union of b to the 0, b to the 1, b to the 2, b to the whatever. So this is the set of all bit strings, right? No matter what their length is. And whereas all of these are clear, it's sort of not super clear. What is a set of strings that contain no elements whatsoever? So I basically have to, I'm just going to declare this to be B0 to be a set. And this is my notation, special notation for empty string. Okay, and now I'm good because this is a set of all 1 elements, bit strings, 2 elements, and so forth, and this is an empty string. Okay, so I can explicitly define the set of all bit strings, but how about this recursive definition instead. So here is the recursive definition of B star. First, the base case that an empty string is in B star, right? So this is the base, and the recursive rule: if X is in B star and a bit is a bit, B is a bit, then XB is in B star. Okay. So now you can see, okay, clearly this is identical to the Recursive definition of B star alternative version. So I have the same base case, and I say if X in B star, then X0 is in B star, and also if X is in B star, then X1 is in B star, right? So this is the base, and this is the recursive rule number 1, and this is the recursive rule number 2, right? It's identical because this one is just more concise, right? Instead of adding X0 and X1 separately, I just take any bit and add XB. Okay, so let's look at the number of applications of the recursive rule and new B star elements. Okay, so if I don't use the recursive rule at all, well, then the only thing in the set is empty. It's an empty string. If I use the recursive rule once, well, what do I get? I have to start with what's in the set. The only thing in the set is an empty string. Then I take any bit and concatenate this X, which is an empty string, with the bit. Well, there's two choices of bits. I basically get lambda 0. Well, that's 0, right? Because there is an empty string. So if I'm concatenating in front, it just vanishes. And lambda 1, which is 1, right? So concatenating an empty string to something is like that thing. I don't have to write it now. Okay. What about two rules, right? So now, well, if my X is again this guy, then I don't create anything new. I'm going to recreate these two strings again. So I skip that. So let's look at X equals 0. Well, if X is 0, I can take any bit, and 0 bit is in a string. So let's do 0 bit 0 will be 0 bit 1 will be. So this is X, this is B. This is X, this is B. And if I take my X1, I'm going to produce these two strings, right? X, B, X, B. So you can see that basically I'm going to have all three-bit strings at this point, etc. Right? Okay, let's I can define functions on recursively defined objects. So here is an object that is recursively defined, bit strings. An empty string is a bit string, and if something is a bit string, then that something followed by a bit is a bit string. That's the definition. Now, here is a function that I will define on elements of B star. It's a length function. So it's a length function. The length function takes elements in B star and outputs an integer, namely length of X is well, length of bit strings X. It's a function f takes bit strings in and gives it an integer where f of x is this. Okay. So it's a funny notation for a function, but it is a function. Okay. How do I recursively define? I recursively define the bit length function, which I denote this way. So a little dot is for an argument. Okay. Base. Length of an empty string I declare to be 0. Recursive is that, well, if I have a bit string and a bit, then length of bit string followed by a bit is the length of the bit string plus 1. Okay, and that's it. Now, this recursive definition works for this recursive of the bit length function on these objects in B star, works with this recursive definition of elements of B star, because there is only two ways that something can be an element of B star. It's either an empty string or it has this form. It's xb, where x is in B star and b is a bit. Now I'm good here, because if is this function well defined on all elements of B star? It has to be defined on all elements in the domain, where there's two cases. Something is in domain if it's in the base, or it's created by some applications of the recursive rule. If it's in the base, then I declare in the base case what's the value of this function f on that element. The other case is that the argument has this form. It's xb, where b is a bit and x is an element of the set. And therefore, and if that's the case, then I do define the value of the length function on such an argument in terms of, well, the value of the function on x. But x is in B star. So this is well defined. If all elements of B star are created by application of either by the base case or by some number of applications of the recursive rule, where it starts from the base case and then, okay, and then uses recursive rules, right? So you can see that this function is going to define, you know, this function f of x for elements. Here it's going to be 0. For all these is going to be 1, because all of these are created by adding a bit to an empty string. So it's 1 plus whatever the length of empty string was, which goes to the base case, that was 0. These are going to be 2, because I use the recursive rule once. So I'm adding 1 to the length of whatever the x was. But now x I already know. These x's, which is either 0 or 1, have length 1. So therefore, these guys are all going to have length 2, etc. Right? And so it goes. Let's use a different example, binary trees. Okay. So here is the recursive definition of set BT. This is the set of binary trees. Okay. And I will do that with vertices that are elements of set A. So this is sometimes often implicit and ignored, but we'll use this set for a while, because I think it might help some people. Okay, so the base case is that an empty string, I'm going to declare the empty string to be a binary tree. And the recursive rule is such: if T0 and T1 are both elements of binary tree set, then so is and A is some vertex so element of set A. Okay, then the following object, which it will be a graph. Okay, it will be basically a picture, if you will. I take A and I connect it with the an arrow going left and down to T0, and I connect also with the line that goes right down to T1. That this object is also a binary tree. Okay, and that's it. So this is my recursive definition of binary trees. Again, these definitions are sort of strangely concise and kind of and at the same time incredibly sensitive to base cases and to exactly how these rules go. Okay, and a slight change in either the rule or the base case means that you're going to generate perhaps a vastly different stuff. And just recall that even if you're generating the same stuff, if you actually write it in code, it might not be, it might be differ in efficiency. All right. Okay, so let's try to see what is it we are generating. So number of recursive rule applications, and these are the new BT elements, and let's use A, which is bits. Okay, so it's just 0 and 1 because we cannot enumerate all possible vertices, right? So we have to, let's just make everything either 0 or 1. Okay, so this is an easy case, right? I just start with an empty string. That's it. Well, what happens here? So I take some bit. Okay, so let's take a bit 0. And T0 and T1 have to be elements of BT. Well, what's in the BT? Just this. So both A and B are equal to the empty string. And this tree I can just represent as 0. Okay, so basically empty strings, I'm just going to skip them. Okay, so this in some sense is like an empty picture. Oh, okay, but that cannot be represented really. Okay, so the only other case I have is start with a bit 1, and that I will just denote this way. Okay, so it's a single vertex labeled with 1, and there's no tree really. Okay, what if I use it twice? So okay, again I have to start with a bit, some element of my set, which is the set of bits, and now I can take, if my T0 and T1 are both equal to this guy, then I regenerate this thing, so I will skip that. Let's say T0 is this and T1 is this. So I'm going to basically ignore the empty strings, okay? And clearly T0 could be this and T1 is this, so I also have this case, which will be this. And also I can do this. So this is this, and I can do like that. So this is this, and I can do the same with 1, right? So what is it that I generate? This tree, this tree, this tree, this tree, and the same with the 1 on top. It's not easy to see these things as trees at all, right? They're kind of pretty degenerate trees. Oh, and that's not it. Sorry, I'm not done yet, right? Because I can start with a bit and instantiate T0 as this and T1 as this.
So this is structural induction, like how you're proving it. This is the inductive
I'm not proving
case.
anything. I'm just
Okay.
constructing a set,
Okay.
right? So this is structural definition. This was my T0, this was my T1, and this was my A. And I can also have this tree. This is T0, T1, A, and this tree, and this tree. And of course, the same for starting with bit 1. So this is the case of the same T0, T1, but my A is now in the second row. My A is bit 1 here, right? So this is my A, and this was my A equals 0 here. So these are the trees that I have generated, where these looked basically kind of degenerate trees, imbalanced trees, but these now finally look like trees, right? So if these are all my trees of depth 2, then you know what will happen if I have if I run it. So how many? Okay, if I run it 3 times, right? So now, okay, T0 could be this and T1 could be this. Okay, so let's take T0 like this, T1 like this, and let's say A equal 1. What did I generate? A, T0, T1. Okay, now these things look like trees now. Let's take T0, 1, 1, 0.
Move down a bit.
Okay. Right. Thank you. And T1, 0, 0, 0. Okay, and A, 0. So what do I get? My A, here T0, which is 1, 1, 0. And here T1, 0, 0, 0. Right? So this is T1, this is T0, and this is A. Right? So here A, T0, T1. Okay, so you can see that this definition, right? Indeed. Okay, maybe running it this many times basically convinces you that this thing is really going to generate a binary trees indeed. Okay. Okay. Let's let's define some useful functions over binary trees. So here is my recursive definition of binary trees again. So recursive definition of binary trees. First, an empty thing is a binary tree, and secondly, so this is the base, and the recursive rule is that if T0 and T1 are binary trees, then for all possible vertices, this object is also a binary tree. Okay, so that was the definition of recursive definition of binary trees. Let's define a recursive definition of height function, of height of binary tree. Call it function. Okay. So it's going to be a function that will take, I'm going to call it function 8, takes any binary tree and outputs this integer that is a height of this tree. I'm going to define it like this. The base case will be that height of an empty string, of an empty tree, I declare it to be 0. And the recursive rule is that for all, no matter what my vertex is, and for all T0, T1 in the binary trees, I declare the height function of the recursively constructed binary tree to be 1 plus the maximum of equals 1 plus the maximum of the height of 3T0 and height of 3T1. It's an intuitive definition, right? Because look, so here is some tree, right? 0, let's say 0. Values or at vertices really don't matter, but you can see that if you wanted to, you could generate this type of object as a binary tree, right? By using this rule, you will, because this is a binary tree, because this is a binary tree, because this is a binary tree, because, and so forth, right? So these are recursive applications. You will eventually go down to these base cases. And so the height of this tree is 1 plus, well, the longer, the higher of these two trees. No, well, this, I know by looking at it that this one is higher. And this is, you know, so here I 1 plus what the higher of these, and this is 1 plus the higher of these two. Well, this is obvious that this one has height 1 plus an empty string, which is 0. So this thing has height 1. This thing has gonna have a higher height, right? Because it's 1 plus higher of the two, which is this one. Well, so cutting to the chase, this will have height 2, this will have height 3, this will have height 4, and therefore this thing will have height 5, right? So this is height 1, this is height 2, height 1, height 3, and I take the maximum. So I take this one to define the height of this whole tree, right? And that's true. 1, 2, 3, 4. Okay, well, because the single object has a height 1, right? Because why is that? Because a single object is created by taking an object and putting empty strings here. So that's 1 plus whatever the height of empty string was, which was 0. So it's 1 plus 0, 1. Okay, so a height of a single vertex, non-empty, right, is a single actual vertex instead of an empty string, is 1. So, okay, let's do a recursive definition of something else, VC function of vertex count of a binary tree. So it's another function, I'm going to call it VC, vertex count, that takes a binary tree and outputs an integer, and it's going to count vertices. Well, base, the vertex count of an empty tree is 0. There's nothing in there. The recursive is that for every A and for every T0, T1, which are binary trees, vertex count of a recursively defined binary tree is, well, I have a vertex here, so it's 1, plus I have some trees here. So I have to count vertices in T0, VC of T0, plus vertices in T1. This is my definition of vertex count. Another function defined over the same domain, but a different function, right? And if you run it on this tree, then the same recursive trace is going to show you, right, that these individual guys have count 1, this will have count 3, this 3 plus 1 plus 1, so 5, and so forth. You're just going to add up all the vertices correctly. Let me try to show that I could now prove stuff about this. So it's 10 to 2, and I'm sorry that I'm going over. Maybe I will ask discussion to do that proof, but whoever can still stay, let's just do this proof now. Okay, so let me bring up these definitions. Recursive definition of a binary tree was that, well, an empty string is a binary tree, and also if T0, T1 are binary trees, basically for any, I'm going to ignore this alphabet because the alphabet really doesn't matter. Then an object that looks like this is also a binary tree. Okay, and then I define two functions. So recursive definition of the height function on binary trees was that the height of an empty is 0, and the recursive rule was that height of anything created like this was 1 plus the maximum of the height of T0 and the height of T1, whereas the recursive definition of the vertex count function was that vertex count of an empty tree is nothing, 0, and a vertex count of a recursively defined tree is I'm adding this vertex and the vertices of both trees. Okay, these are my definitions. Let's consider the following claim, which is that for every binary tree, the following is the case. If I look at how many elements, vertices a binary tree could have, it is upper bounded by an exponential to the height of the binary tree. But to get this right, I have to add a 1 and subtract a 1 here. Okay, well, look, I mean, sort of sanity check. Okay, like give yourself some tree. It has vertex count is 3, height is 2, and indeed wait. Am I stating this correctly? Where is my claim? Hold on. I'm a little lost in my notes. So wait, so I declared this to be height 2. No, so it's like this. So a height of an empty, because height of an empty, yes, is 0. So it's, yes. Yeah, okay. So this is height, height is 2, and indeed 3 is bounded by to the 2 minus 1, right? Because this is 3. Okay, I mean, even simpler. So let's take a single vertex, right? So vertex is 1. There's only one vertex here. The height is 1, and 1 is bounded by to the 1 minus 1. Oh, wait. No. Hold on. What? Oh, yes, of course, right? So this is 2 to the minus 1, which is 1. Okay, good. An empty string. The vertex count is 0. Height is 0. 0 is bounded by 2 to the 0 minus 1, which is 1 minus 1, which is 0. Okay. So in fact, this sanity check is more than sanity check. This is the base case. So this is the base case of the proof. Right? So the proof goes like this. I'm claiming this is true for all binary trees. There are 2 types of binary trees. Either whatever is declared as a binary tree as a tree, or it's created using the recursive rule. So let's prove it first. For the statement is true for everything created by the base case. Well, so okay. So formally, what's the base case of the proof? If T is empty, so T created by base case, then the height function on this T is height of empty, which is 0, declared by the base case of the recursive rule for definition of height. And VC, the vertex count of this tree, is declared by the base case of the recursive definition of vertex count. So this is VC of empty string, which was also declared to 0. And indeed, it holds that VCT, which we said was 0, is bounded by 2 to the height of T, because this is 0 as well, minus 1, because this is 2 to the 0 minus 1, which is 1 minus 1, which is 0, and it's true that 0 is upper bounded by 0. Okay, so that's the base case. First part of the proof. Okay, what's the rest, right? Well, T is created somehow this way, right? So this is by the recursive rule. Okay. Okay. Well, in that case, VC of T is, by the recursive definition of the VC function, the same as 1 plus VCT0 plus VCT1. And now by what I'm going to call a structural induction, induction hypothesis, I will assume that the statement is correct for all objects in the set that I created by fewer number of applications of recursive rules. So let me assume that the statement is true for all these building elements, T0 and T1. So therefore, by this structural assumption, this can be upper bounded by 2 to the height of, so this is 1 plus, and now I'm upper bounding VC. So let's say that this statement, this one, holds for both T0 and T1. What does it mean that it holds for T0? Well, it means that VC of T0 can be upper bounded by 2 of height of T0 minus 1. And this also means that the VC of T1 can be upper bounded by 2 of height of T1 minus 1. So, well, this is, of course, this is the same as 2 height of t0 plus 2 height of t1 minus 1, right? Because I have plus 1, minus 1, minus 1, so it's minus 1. And this is upper bounded by twice the maximum of the two. This sum is upper bounded by this because, right, whichever of these two is bigger, a plus b is at most twice the larger of a plus b, and minus 1 carries, right? So now max of 2 to the something and 2 to the something else is the same as 2 to the max of the 2. So it's height of t0 and height of t1 minus 1. And this, just by arithmetics, is the same as 2 to the max of height h2 height t1 plus 1, right? Because I multiply by one more 2 minus 1. And now what do I know? What does this look like? This thing, by the recursive definition of the max function, of the height function, sorry, this whole thing, right? Sorry, I'm running out of space, can be rewritten as 2 to the height of this new tree, which is t, height of t minus 1. And so I am now happy, right? Because I have shown that VC of t is less or equal to the height of t minus 1, which is my goal. Okay, sorry for running out of paper at the end. If you have some questions, you ask, please speak up.
Did we go over how many, you know what big O is, right? Big O?
Yes, but I have not used it. And let's not introduce this because it's a whole different story. I don't want to confuse people who never seen asymptotic notations. It's not needed.
It showed up in my discussion yesterday.
Sure. So good. So, if there is someone who would want me to go over something about this proof that wasn't quite clear, then say so.
Are we going to be using, so with the strong, and I mean, not the, so with the, which induction are we going to be, which induction would you use for this one? For like algorithms like these, recursive algorithms?
Well, it's called structural induction.
Structural induction.
But it's really nothing else than a standard induction where the natural parameter is n, is the number of applications of recursive rule to create something. So if you think of this number of recursive rule applications as an induction parameter, then this is really standard induction. But then you can forget about that and just think of this as a induction which basically works like this. If this statement is assumed true, if it was true that this statement is true about any two elements of the set, then you need to prove that if the statement is true about these, about these elements, then you have to prove that it's true about this one. And you have to do it for every, if there were more recursive rules, then you would have to prove it for each one. So what we were proving in the induction is if the predicate holds on T0 and predicate holds on T1, then predicate holds on this construction. And here the predicate was this. P of T was this. Okay, this thing is a predicate. right? It's either true or false over for any t. This bound is either true or false, right? So it's a predicate. And this is what you're proving in structural induction. Why? Right? So this is the recursive case, and first is the base case that P of whatever base case was has to hold, right? Now the form of these two statements will depend very much on what is the recursive definition of an object, right? The base case of the proof has to correspond to base case of the object definition, and the recursive case has to follow the recursive rule.
So could you just state this in pretty much words instead of using a P of K and then a P of K plus 1?
It's not P of K plus 1. This is it's a P of this recursively defined object that you're proving.
Okay.
But if you think of K as a number of recursive rules, then you can think of this as P of K, and this is P of K plus 1. But you're changing the nature of the predicate. It's no longer about applies to trees. It applies to integers. And the predicate says every tree created by up to that integer number of applications of recursive rule satisfies this bound.
Okay, but can we also, like, for an example, like, let's say, like, there was this one homework problem, like, I'm not going to be too specific on it, but I'm just going to, like, mention, like, I'm just going to go into a tiny bit of it. So I specified a base case, and then I was in the inductive case is like, let's say for a like a certain set, like this number of iterations will happen. Then I proved P of K, then P of K plus 1, and then I said for P of K plus 1 it can still be made with P of K, but then you're going to have to do a certain number of more algorithms, like 2 times or 3 times more. Did something along those lines work too?
You know what? No, I lost you. So hold on a second. So basically, I have to go.
Okay.
It's past the time. Is there any other person who have some quick question?
I had a quick question. So Zybooks is like not really working for me too well. Like it's hard for me to learn from it. Do you have any recommendations on other things to use to like any other
textbooks? No, I don't have right now. I mean, did you show? No, I mean, did you? So what do you mean that it's hard for you? Like, you don't understand?
I mean, nothing's like explained in like plain English. It's all formulas, and like that's kind of hard for me to learn by. So I don't know. I've already looked up other like resources, but I just wondered if you had any particulars.
No, I didn't. I didn't think of that. I mean, you know, posted on Piazza that you're looking for other resources, some alternative write-ups, some more intuitive write-ups of this stuff. I mean, maybe somebody, you know, took a class with some other notes. Maybe somebody will pipe in with some links. Maybe a TA would know. I mean, of course, there's tons of books about this, right? We used to use a different book before this by Rosen. I mean, but I don't know if it's any less formal than Sandy Irani's book. And it's not, you know, I don't know how to get a free copy, right? But I can post the textbooks I know of. They're famous and used all over the place.
Okay.
Yes, so, but, you know, I'm not sure how you can get it, you know, except of spending $100 on like getting that book and checking whether it works for you.
All right. All right. Thank you.
But post it. Maybe it will, maybe, you know, there's 200 people here. So anyway, then we'll just all remember that to look for stuff.
Okay. Thank you.
Professor?
Yes.
So for today's homework,
I will
for
stop
the
recording
first-
actually.